Hey everyone, welcome back. Let's get started right away on discussion 9. We're talking about textbook page 179, problems 16 and 17. So essentially, we have a treasure chest filled with a mass with a long rope tied around it. Its center lies in the middle of a room. That's what we're told. I'm just reading from the book here. I'm not showing the screen today because I'm trying to keep this more brief than normal. Essentially, we're pulling on a heavy chest with a rope. And so if we draw a free body diagram here, mass M, let's move this down here. We have a rope. This is going to be our applied force. And we're told it's at angle theta. And these will be our components for our applied force, Fty and Ftx. Okay, this should look pretty familiar, I think, by this point. So this piece here, this is our rope. Okay? It's also this is where our applied force is. So now we need to look at our other forces. We have a force pushing up off the ground onto the box. That's going to be our normal force. And we have a weight force that's pushing downwards from the box itself. And then as this thing is being pulled this direction, we have some resistance. We're told friction coefficient, static friction coefficient is mu sub s. So that's going to give us a force pushing this direction, in the opposite direction, right? So this is going to be F mu sub s. So we're told that we want the tensile force, and we want it in terms of M mu sub s theta and g. Okay, just making sure I can read that right. Okay, so we want the magnitude of the tension force in terms of M u sub s theta and g. Okay, so well, let's start by summing up all of our forces, and let's do it component by component. So what I mean by that is let's do it, let's sum up the y components first, right? So we can see that this normal force and this weight force are going to cancel out because we're told that it's just being pulled along in this direction, right? And all we have really is some resistance here. This is not jumping up or down. So what I said before is not explicitly true. We actually have this y component of the tension force as well. So we have 1, 2, 3 for y components. So let's write this down. I'm going to say resultant in the y direction is going to be normal force minus the weight force plus the tension force in the y direction. Okay? Also, since this thing is not jumping up and down or breaking through the ground this way, it's not going up this way or this way, we can say that the overall magnitude is going to be 0, right? Or the sum of these forces is 0. So what do we have here? So this y component here, since this is angle theta, this is going to be Ft, because that's the magnitude of this here, Ft sine theta. So that's our y component. So it's going to be Ft sine theta plus the normal force minus the weight force. And the weight force, as usual, is mg. So that gives us we don't know what normal force is going to be, and we don't know what Ft is going to be. So we need it in terms, we're going to solve for Ft, so let's put this in terms of Fn. Let's see if we can make sense of this. See if we can do something with this, with the x equation. Okay, so next, let's do the x direction. So we're going to have, what do we have? We just have x component here of the normal force, of the tension applied force, right? So this is going to be Ft cosine theta. And then we also have this frictional force here going this direction. That's F sub mu, and that's usually the frictional coefficient times your normal force, right? So let's write this down. So we want to know what the tension force is just when it starts moving. So we want this thing to be in equilibrium, and then we're going to break that equilibrium by increasing the tension force. So I'll show you what I mean. So we have our tension force in the x direction. It's going in the positive direction this way, right? It's going this way. This is going this way. Now, so this is traveling in the positive x direction. This is resisting in the negative x direction. Okay, so that's going to be negative mu sub s. Let's rewrite that again. So this is Ft cosine theta minus, remember this is the frictional coefficient times the normal force, okay? And like I said, we want this to be in equilibrium, and we want to figure out what the tension force is going to be to break that equilibrium and get the box moving. So we can use the information we just found, right? Since this is equal to 0, we can say that Ft cosine theta is equal to mu s Fn. And remember, we had this was equal to Fn over here. Here we have Fn as well. We can let's set this equal to Fn, this equation, and then we'll set these two things equal to each other, right? So what I mean is this. Let's say here now we have Fn is equal to Ft cosine theta over mu sub s. Okay? Now that's all going, let's set these two things equal to each other. This is equal to this. Okay? No, sorry, we don't need to do that. Let's do a different thing because that's unnecessary. We already know what Fn is. Fn is this, right? So let's just plug that in. That'll make things a little bit easier. We don't need to go through that other process. So this is going to be mu sub s times mg minus Ft sine theta. Okay. So now we want to solve for Ft. So Ft cosine theta. So now we just do a little bit of algebra. This might take a moment. Mu sub s mg minus mu sub s Ft sine theta. Then we take this to the other side. We are left with Ft cosine theta minus mu sub s sine theta is equal to mu mg. This is mu. Okay, that means that Ft is equal to mu mg. Drawing a mu is hard. Mu m, there, that's a pretty good one. Mu mg cosine theta minus mu sine theta. This is also s. All of my mu coefficients are mu sub s. They all are the same coefficient, just in case there's any confusion. So it's maybe I'm being a little sloppy. I'm trying to be as explicit as I can. There we go. So that's the answer. This is what the tension force is equal to. Oops. Oh, come on. And there we go, something like this. Okay. So now all we have to do for the next problem is plug in some numbers. We're told, well, read number 17. There's a whole bunch of information in there. And then what happens is we do this. 0.52, 375, 9.81 meters per second squared. And you want to check all of your units as well. And we can do that. We can do that together. Then we're going to have, we're told that the angle is 30 degrees, so that means cosine theta is square root of 3 over 2. There's the coefficient again. This is going to be 1/2 because sine of 30 degrees is 1/2. This all comes out to be 1698.851 after I plug it into my calculator. So check that. And then 1.698 times 10 to the 3, or we can just say it's approximately equal to 1.7 times 10 to the 3. This should be in newtons. Let's double check that. So we have this cosine theta term and the sine theta term. Those are unitless. This coefficient is just a number. That's also unitless. And then we have a mass, kilograms times meters per second squared. Kilograms meters per second squared. That's a newton. So our units of newton work out. So this is the answer that I found. Okay. Problems 19 and 20 on page 179. We're told that we have a sled and a rider. So there's somebody sitting on a sled and it has a total mass m. They're at rest on a snowy hill, so the sled is not going anywhere. There's a coefficient of static friction between the sled and the snow. We want a maximum angle of the hill slope in terms of the static friction. How does your answer change if the rider is not on the sled? Okay, so pretty much, let's draw a picture of what's going on here. So we have a hill, and there's a sled and a rider. This looks more like a surfboard, but you know, you take what you get. So let's see here. So now let's just say that this is some mass, right? But that's not good. The picture isn't good enough. So let's approximate this more as a box, because we've done a lot of box on ramp problems. So now let's do something like that. So here's mass. Okay? We want to know what is the maximum angle. So like how high, how steep of a slope does this have to be before this box, before this box slides down the ramp, or the sled and the rider? So this guy is just standing on this surf sled here, and he wants to go, but nothing's happening, right? There's a static coefficient of friction, right? Something like that. And so we want to raise the hill, if that's even possible. We want to raise the hill so that this angle is steeper and this guy goes down the hill and has fun. Okay, so I'm gonna get rid of this. Let's just move this weird drawing. Okay, now let's draw our free body diagram. Okay, so we can safely assume that this sled and rider combo is not jumping off of the hill or breaking through the bottom of the hill, right? I'd say that's a fair assumption. Nothing is going on. Like, we are only talking about friction going this way and the sled and rider going this way. Okay, so let's get back to what we know from before. We have a gravitational weight force pulling this direction, right? We know that this is theta from before, because this is beta, and because this is 90 degrees here, this is 90 degrees. Beta plus this angle must be theta, right? Because this is 90. This and this are 90, and this is 90, that's 180. Okay, just as a quick reminder, if you don't remember how we got that. I did go through it in a lecture. I think it was the last lecture or the one before. But okay, so next, so now we have this is our weight force y component, and this is our weight force x component. that indicates that we have set this as our y-axis and this as our x-axis, right? Okay, what's next? So now we have a frictional force pushing against the direction we want to go. Try to get that mu. And then we have the weight force in the x direction. Okay, now one thing is for sure, we're told that the sled and the rider are not going anywhere. So now we can set up the resultant force in the x direction as 0 because we have no motion. So we have no net force, okay? So then we have x minus the frictional force. This is weight force in the x direction here, going this way because this is parallel to this, minus going the opposite direction, the frictional force, okay? We also know that the thing is not jumping. This combination of sled and rider are not jumping off of the hill or breaking through the ground. It's just sitting there. So that means that we have 0 in the y direction, and then so that's normal force minus the weight force in the y direction. Okay, so let's start setting some of this up. So now we have mg cosine theta is equal to, I'm doing this by the way, right here, this one. Mg cosine theta, this is the weight force in the x direction, oops, sine theta, because here's theta and this is sine theta, right? So got to be careful there. Mg sine theta is equal to the frictional force, right? So the frictional force is the frictional coefficient times the normal force. Okay? Cool. That's some useful information right there. So recall that we're after the angle. I just want to solve the y version before we move on. There are a few different ways we could approach this, but I want to make sure that I'm more methodical here. So now we have the normal force is equal to the weight force, which is going to be mg cosine theta, right? Because this is the y direction that we've defined, and this y component of the weight force is cosine theta, mg cosine theta. Okay, cool. So now we take these two equations and we combine them. So we just plug in this into here, right? We plug this thing into here, and then we bring it all down. So let's just rewrite it. Mg sine theta equals mu times mg cosine theta. So what cancels out? Well, this is going to cancel, this is canceling, and that cancels, and now we are left with 1 is equal to mu s 1 over tangent. Actually, let's do it this way. Let's do it a different way. Tangent theta is equal to mu s. That speeds things up quite a bit. So what does this mean? Now, since we're looking for the maximum angle, and this is the angle in equilibrium, by the way, that's what we've been after the whole time. Determine the angle in equilibrium, then we can determine like if anything is increasing beyond the angle of equilibrium, it's going to slide down. Okay, so that means that theta is equal to the inverse tangent of the frictional coefficient. Let's rewrite this. Let's make it clear. This is the answer. This is your angle that we're after. So let's just recall how we did this real quick. So we drew our free body diagram, right? We first drew a picture of what's being described in the problem. Then we approximated it as a free body diagram. We're told what forces we have. We have a frictional force. We know we have a weight force. There's an incline. This is a ramp on an incline problem. There is no action happening in the y direction. There's no action happening in the x direction. So we can use that sum up our forces in the x direction. This is equal to 0. Sum up our forces in the y direction. This is equal to 0. Then we break it all down, right? The weight force is mg sine theta is equal to the frictional force is coefficient times normal. And then we do the y direction, right? Normal force is equal to mg cosine theta. We plug that back into our equation, and we solve for theta. Okay? All right, and then there's another part of this where it's similar to the last one, where they just give you values. But before I move on to that, I should note in 19 it asks, how does your answer change if the rider is not on the sled? Well, I mean, if we go back to where we had set up our equation to find the maximum angle, or our angle in equilibrium, this was the max angle that we could hold onto the hill, right? Or that the hill held onto the slider. No, what is it? Rider and sled. Okay. What I'm saying is, once we set up this equation to solve for the angle, mass and gravitation went away. These terms went away. So in our final equation, all we're left with is the inverse tangent of the coefficient. So this doesn't depend on mass at all. So when it asks, how does your answer change if the rider is not on the sled? Well, it doesn't. It doesn't change. So the sled will still go down. Even if it's just a lonely sled on a hill, and we increase the angle to be greater than inverse tangent of the coefficient, this thing is going to slide down. Okay? All right, next part. Here's where we just plug in what they give you. You're given a frictional coefficient, you're given an angle. Okay, let's plug these in. So now we have theta is equal to inverse tangent of, it tells you that the frictional coefficient is 0.225. That gives you a value of 12.68 degrees. That's what I just got. And then it says if the angle is 19.5 degrees, what happens? Are they at rest? Well, we just found out if this is the frictional coefficient, this is our angle, right? So here is 12.68 degrees. That's way higher than 12.68. Let's try it. Something like this. That's theta. So we're going to slide down the hill if the angle is higher than this. If it's any higher than this, we're sliding down the hill. So since it's 19.5 degrees, then yes, we will be sliding down the hill. Okay, moving on. Okay, so problem 29. We are given another sled and rider problem. It's pretty similar to the last one, but in this case, now instead of the sled and rider being stuck on the hill, and we're trying to figure out how to increase the angle to make them slide, this time the sled and rider are sliding down the hill, and we want to know what the acceleration is. Okay, so it's another essentially block on an incline. Wow. The thing about this that's interesting to me is that, I mean, yeah, I'm setting it up as a block on an incline problem, which is rather boring conceptually. I mean, what we're really talking about is something that you can witness in the real world, right? I mean, you wouldn't find this sort of weird sled like this probably, or someone standing on it, but you know, I mean, people slide down hills, you know, and lots of stuff happens where things slide down inclines. So you can take a real world problem like this and model it with a free body diagram and actually determine things about it that can help you, which I think is pretty neat. All right, so here's our mass. Let's recall our free body diagram for this type of situation. pretty much we have the same setup. I'm just going to put this in gray. This is the weight force pulling down, right? Which gives us a y component. We'll call this y, and then an x component. Okay, and then we have frictional force. This is a kinetic friction because we're sliding. This is supposed to be parallel to the other one, something like that. Okay. Okay, so since we're just sliding down a hill in a pretty basic setup, let's recall that the normal force is going to equal the weight force in the y direction, right? So here's our theta. Okay, and this is F sub the y component of the weight force. That's what I'm trying to say. This is the normal force. This thing is not jumping off of the hill or breaking through the ground, so that means that the y component of the resultant is going to be 0. So 0 equals F sub n minus F sub y, because these are going in opposite directions, right? This is going up, this is going down. So that means that we can set the normal force is equal to mg cosine theta, because this is cosine theta here. Okay, let's do the x direction. Okay, so now we know that we do have a net force in the x direction because we're in motion. We're told we're in motion because we have kinetic friction. Kinetic friction implies that you're in motion and you have some resistance. Static friction implies that you are not moving. Okay, so since we have kinetic friction, we're moving. And since we're moving, we have a net force in the x direction. So we're going to say m, mass of the sled and rider, times the acceleration in the x direction is equal to, what do we have? We have the weight force component in the x direction, and then the frictional coefficient, frictional force, excuse me. So this is going to be mg sine theta minus, remember that this is going to be equal to the coefficient of friction times the normal force, right? And what does that mean? That means since we solved earlier in the y component here, Fn is equal to mg cosine theta. So here we'll put this mg cosine theta, and this is all equal to m a sub x. Okay, well, we can see that the m's are all going to cancel out, right? A sub x is equal to, let's just pull this g over here, sine theta minus the frictional coefficient times cosine theta. So we're actually given these information. We know what this is, g. We know what g is. We know what theta is. We're told that it is 19.5 degrees. We know what the frictional coefficient is. We're told it's 0.195. So we can actually solve for this. So this is going to give us g times 0.149. I just plugged all of this in. All of the information, if you were unaware, is in your book. On page 179, we're doing discussion problems 29 from the book, and 30, I believe. 30. Okay, so this is going to be approximately equal to g 0.15. I may have made a mistake. Well, I wouldn't call it a mistake, but I'm rounding early, so that's something you might want to double check. I'm just kind of going through this quickly so you can see sort of what the answer is. I would say check this again, because like I was just mentioning, I rounded this early. Sometimes it affects the answer. I got 1.47 meters per second squared. That's the acceleration. That's your answer. And then we also have a question. Is the acceleration greater, less than, or equal to your result if a more massive rider uses the same sled on the same hill? Explain. Well, no, it doesn't, because, I mean, it's going to be, the acceleration is equal because it does not depend on mass. Recall that when we set up our equation to solve for acceleration, we completely got rid of mass. So again, this does not depend on mass whatsoever. So acceleration does not depend on mass. So if you took a more massive rider and put him on the sled, he's just it's gonna be the same as if you took him off completely, given the angle and the frictional coefficient. Okay. Next problem, we're pretty much given the same problem. So number 30, it's the same setup, but in this case, they change some of the numbers, and we're told that we're accelerating at 0.7 g. So let's set this up. So we're told that the acceleration A is 0.7 g. We're given a mass 56.8 kilograms, and we're given the coefficient is equal to 0.18. We want to find theta. Yeah, so okay, so let's set this up into an equation that we can see more clearly. 0.7 g is equal to, this is from earlier. By the way, I'm not doing anything differently than what we did just in the previous problem. I'm just taking this equation and plugging everything in, because we've already found all of this stuff, so we don't need to go through the whole process again. 0.18 times cosine theta. So the general idea here is that it's going to be incredibly difficult to solve, if I can get this, to solve for theta, because these are coupled, right? We have sine theta and cosine theta together, so that's going to be pretty tricky to do analytically. So what we can do, sorry, I'm just noticing, oh, one thing we can do here, 0.7 is equal to, okay, so now we don't need g anymore. We just get rid of that entirely, right? Cosine theta, that's fine. Okay, so this is what we have to work with, and this is what I set up. So pretty much what I did was, it even recommends in the problem, use a spreadsheet. Okay, so what I did then was I put into a spreadsheet from 0 to 90, essentially. Okay, I don't have all of that here, but it's pretty easy to do. So I entered this equation here. I want to find where this is going to equal this. Where does this equation equal 0.7? That's what I did. So here I entered in the equation, you can see. I don't know why that came out as a square. Anyway, you can see that. And then so let's find, where does this equal 0.7? Well, the closest thing that I see is right here at about 54 degrees. Okay? That's your answer. The angle of the hill is 54 degrees. I don't think that you're going to have to do this on the WebAssign, but if you do, you just have to find a way to enter in this equation. It's not that hard. I mean, if you need help, let me know. Okay. Okay, the next problem, number 68, we are given a conical pendulum, which is a pendulum that instead of swinging just back and forth, just this way and this way, it actually does, it's like circular, so it's actually going to trace out like a circular pattern this way. Okay, that's not a circle, more like this. Yeah, there we go. Let's put this, there we go, that looks much better. Something like that. I'm trying to get this to be sort of reasonable, but it needs to be much smaller. Okay, so it's going to kind of trace around this way. And this way. It's going to go in a circle, right? So that's a conical pendulum. And so anyway, it says it gives you a bunch of information about the pendulum. It makes an angle here of theta. So let's say theta is equal to 7 degrees, which is a pretty small angle. That's actually a really, really small angle. You're told the mass is equal to 0.21 kilograms. You're told that the length of the thing is 12 centimeters. So that's why this is a very small, it's like a toy or something. All of this is super small. So this is something you could put on your desk. So here's our angle. What we have a tension force, right? This is also going to be our centripetal force. This is a tangential force. And it's not one-dimensional. It's actually pulling upwards, right? This is going to be Fty, and it's also pulling back towards the center of the origin in the x direction, okay? Provided that we define our axes this way. This is x, this is y. Okay, so we also know that this is going to be theta. What else do we know? We know that this is m, this is our mass, and we know that because this has mass, this has a weight force, so this is mg. And that's pretty much it. So we have essentially just two forces acting on our bob, our pendulum bob. Let's do blue. I like to do blue for our forces. Okay, our components can be black or red or whatever, but the main thing here is we have this tension force and we have a weight force, and that's pretty much it. So let's find what is the y component. Okay, so we have Fty minus mg, let's say, right? This is going to equal Fty is going to be, we have Ft cosine theta minus mg, right? That's our y component. Now, one thing we can do is we can say in equilibrium, these two things are going to be equivalent, right? And since those are the only two y component forces that we have, let's see here. Let's just put this in equilibrium. Now it's the tension force is only a y component force, right? There is no x direction tension force. So in this situation, we have these two things are equal. That means that, what do we have? We have Ft cosine theta is equal to mg, which means that Ft is equal to mg over cosine theta in equilibrium. So anyway, this puts us at, what is this? 2.07 newtons in the y hat direction. That is the y direction, and now we want the x direction, right? So this is just going to be Ft sine theta. Let's go back to our diagram and look at what I'm talking about. This is our tension force, and this is Ft sine theta, right? Here's theta, Ft sine theta. Now, what does that equal? Well, sorry, this something right here, this is actually not explicitly true. This is here. So this is actually equal to the tension force. This was in equilibrium, right? But now that we have an angle, we have to account for that. So here, this is going to be equal to 2.07 newtons sine 7 degrees. And this is a really small angle, okay? So we would expect this to be a pretty small number, because we don't really have any deviation from the origin. We just have, let's see, if we go back up here, let's just use the first diagram because this one looks better. So let's say this is only a 7-degree angle. If this thing just comes out 7 degrees, the x component force, the overall x component force is going to be rather small. Okay? So what does this equal? This equals 0.25 newtons. So the x direction of the tension force is equal to 0.25 newtons x hat direction. Now let's go back to the y direction. What do we have? We have, okay, we want to know what this is, right? Because we're asked to find the components. So this is going to be Ft, which we know is 2.07 newtons, cosine theta, which is 7 degrees. So what does that give us? So Fty is equal to 2.07 newtons times, what did I say, cosine theta, which is 7 degrees. That's going to equal 2.05 newtons in the y hat direction. Again, it's because we're almost exactly equal. So like here we have 2.07 newtons is what we had in the y direction, and now we're still pretty much at the same value because we haven't really deviated too much from that original position. Okay, so that's it. That's what we have. So here we got 0.25 newtons x hat plus 2.05 newtons y hat. All right, next, we're asked to find the radial acceleration. So let's go back to our diagram real quick. Where is our radial acceleration pointing? It's pointing in, right? This is radial. It's pointing along the radius. So this is also our centripetal acceleration. So we want to find this. So this is, if we look at this diagram, it's not going to have anything to do with the weight force. It's not going to have anything to do with the y component of the tension force. It's only going to be due to the x component of the tension force. This one. Okay, so let's use that. So what do we have? Let's go blue. We have, where's our x component? So Ft sine theta, okay, so that's what we have for our x component. So Ft sine theta is equal to mass times centripetal acceleration. The reason we have a mass here is because this is a force, right? So force is equal to mass times your acceleration. But looking at this, we actually don't need that. What we can do, I think that's easier, is we can just take, we already know what this value is, right? So we can just take this value, which was, what was it? It was 2.25. Yeah, let's start there, 0.25 newtons. And then we need to divide by the mass because we're just looking for the acceleration, right? See what I'm saying? So this is going to be, this value is equal to mass times acceleration. So mass times acceleration is equal to 0.25 newtons because we're in the x hat direction. This is the x component of the tension force. We found what that is. Now let's just divide by the mass, which we know is 0.21 kilograms. This is going to give us a value of 1.19 meters per second squared, which is approximately equal to 1.2 meters per second squared. Okay, so just to recap on that, I took the, let's see, where is it? The x component, here it is. The x component of the tension force is going to give us our radial acceleration here. Oops. It's going to give us our radial acceleration here. Okay, that's Ft sine theta. Recall from up here, sine theta, right? Here's theta, Ft sine theta. This is from our free body diagram. So we plug that in. Ft sine theta is our x component. Ft sine theta, we know what this value is. Set it equal to mass times acceleration. So then we just divide by the mass. Okay, so we take 1 over m on both sides. That gives you your value. Okay, thanks for watching.